Okay, now recording. All right, so we're going to do spherical coordinates today. Oh, that doesn't look very good at all somehow, but I'm not sure what I can do about it. I just have to do my focusing thing. I'm up to 15.8, which is on spherical coordinates. I'm going to include one more problem, 27, but I'm probably going to end up doing it anyway. Okay, so on the homework list, put in 27 as one more additional problem. Okay, I might sneak in a little bit of 15.9, at least the early part of it, the part that's not that quote unquote bad. Okay, I'll save the so-called bad stuff until later. So we're almost done with the chapter. So for sure, 15.8 today, spherical coordinates, another coordinate system. 15.9 is on change of variables in multiple integration. Okay, and then I would have be able to finish chapter 15 by next week. Okay, so in schedule wise, let me write this down. So I guess I got up to 15.7. Okay, so we're here 15.8. Maybe some of 15.9. Give you a quiz on triple integrals, and that's it. Okay, so we should be finished plenty of time for the exam on the 22nd. Is that right? So most likely I'll get started with chapter 16 here. Okay, again, I'm not as far ahead as you might think because I'm not going by this schedule anymore. I'm trying to finish everything by what, Tuesday, the 11th of May. And then last regular test on the 13th. Just a Q&A session on the 18th and then final exam on the 20th because of the change in what I had before. Okay. All right, so another coordinate system in 3 dimensions, spherical coordinates. So we have our regular rectangular coordinates. So dv is dz, dy, dx in some order. dz, dy, dx is our so-called favorite. Okay. We had cylindrical coordinates last time, which is really just polar coordinates and then leave z alone. Right? Where instead of x, y, z, you have r, theta, and z. And even, right? Okay, and here are the conversion formulas, which is basically the same thing as you had in polar coordinates and just leave z alone. X is r cosine theta, y is r sine theta. R squared equals x squared plus y squared, tan theta is y over x. Okay, so now we have spherical coordinates. Page 1045. You know, the focus on this is so bad, so much worse than before. I'm not sure why. Unless I might have to raise the book up even higher.
Is there any way you can like clean off your camera or restart or something? It's like we can't see like anything pretty much.
Yeah, I can't either right now. For now, I'm just gonna have to do the raising up. I don't think it's a camera. I mean, issue. It's focusing on this thing. But yeah, if worst comes to worst, I'll just raise it up as I need to. But triple integrals. All right, so see that point out in space, point P? The 3 coordinates are 1 distance and 2 angles. So the 1 distance is the Greek letter rho, that funny looking P, rho, theta, and phi. That 3rd coordinate is phi. Okay, so 1 distance, 2 angles. Okay, now what do we have? Well, of course, x, y, z, you're comfortable with that. It's 3 distances, an x distance, a y distance, and a z distance. Cylindrical coordinates, we had 2 distances and 1 angle. Right, r, theta, and z. R and z are distances, and theta is an angle. Here you have 2 angles. Now, see the theta? Theta is the exact same theta as you had for polar coordinates / cylindrical coordinates. What's new is rho. Rho is the distance away from the origin in space, which is not the same as r. R was only in the xy plane. Phi is new. Phi is an angle made with the positive z-axis. So see that phi there? Okay. So theta is the angle that's made with the positive x-axis. Phi, or sometimes phi, that's the angle that's made with the positive z-axis. Okay. Now the thing that's a little bit tricky about phi is you're probably not used to it. It's not the same as angle of elevation. So in trig, when you had angle of elevation, you're looking up like so. Okay, then you would think of this angle, but it's not. You have to actually start straight up. Imagine you're looking directly up into the sky, and then the angle that we come down right here, that's phi. And the thing that makes it a little bit uncomfortable, of course, is the way our eyes are. Our eyes go this way. Now, if your eyes were on literally the top of your head, okay, go straight up, then you would say, okay, that's normal, but it's not normal for us to do that. I mean, normally when you look up at an object in the sky, you think of angle of elevation going this way, okay? But the reason why they do it this way is we can have the angle starting from the positive z-axis. It's very similar to theta, positive x-axis. Okay, so phi is not the angle of elevation. It's actually 90 degrees minus that. Okay, so you have to imagine, start by looking straight up the positive z-axis and then coming down a certain angle. Okay, so we have rho, theta, and phi. Rho, theta, phi. Okay, and I'm going to experiment with this a little bit more, although I might regret it. Can't even get it straight now. Try that. I'm not sure that helped. Okay, rho, theta, phi. I will superscript with S for spherical. So now when you have an ordered triple, if you're not sure what coordinate system you are, I'll superscript. Superscript means writing above like an exponent. Okay, so if I put R, rectangular coordinates. I did that last time, right? C for cylindrical coordinates, and S now for spherical coordinates. Okay, now, some things that you want to look at here. Yeah. The reason why it's called spherical is if you have an equation, figure 2 on page 1045. Okay, if you have rho equals a constant, it's a sphere, like rho equals 3. You're saying, give me all the points that are 3 units away from the origin. So that gives you a sphere. That's why it's called spherical coordinates. Okay. Theta equals a constant, gives you a half plane. So see where they have the letter C there? Theta equals C. And then take any distance away that you want, and you end up with a half plane. What's interesting is for figure 4, if phi equals a constant between 0 and 90 degrees, pi over 2, you have a half cone. Technically, that's a half cone. A full cone as well has the bottom part. So if you include the top and bottom part, that's considered a cone technically in some circles. Okay, so it's a half cone. So if you can imagine, I'm not sure if it'd be better if we met face to face, but you start going straight up, come down a certain angle. Let's say I'll go down 30 degrees. Let phi vary from 0 to infinity, so we go all the way there, and let theta swing around from 0 to 2 pi. So if I swing that around, you can see the cone, right? Hopefully, it swings around. So again, start 0 degrees or radians is straight up for phi, not what we normally think of, because of the way our eyes are, we like to go that way. But you have to pretend your eyes are on the top of your head going straight up. Okay, so you come down an angle. So let's say phi is 30 degrees, I come down 30 degrees. Okay, and then as I let theta move from 0 to 2 pi, can you see that you swing around and you end up getting the cone? that thing right over there. Okay. And yeah, you're right. It does seem blurry no matter what I do here. So there might be something wrong with the lens here, but I'm sure I can correct that now, but in the event. All right, so equations you need on page 1046. It's almost like I'm going to the eye doctor here. All right, so let's look at this picture here. See the rho theta phi in red and x, y, z. Okay, the phi by definition is, yeah, can't really do both of these. This angle right here, C phi. They have another phi right over here. It's because those two angles are alternate interior angles. Do you remember from high school geometry? If two parallel lines are cut by transversal, alternate interior angles are congruent. Remember anything like that from high school geometry? So see the two phis, one's in black and one's in red, they're congruent because they're alternate interior angles. You see rho there. Okay, see the r down at the bottom? That's the same as the r that we had in cylindrical coordinates, right? So you see r there. All right, so a little bit of trig. Okay, z is rho cosine phi, because this is the adjacent. Sorry, I know you can't see it. That's the adjacent. That's the hypotenuse. So cosine of phi, adjacent of hypotenuse is z over rho, which basically means z, if you clean up the algebra, you get z is rho cosine phi. Now look at r. Okay, for that right triangle that's there, this one right here, it's a right triangle. The sine of phi is opposite over hypotenuse. That would be r over rho. That means r is rho sine phi. Okay. Yeah, I don't know if I'm going to survive this, folks, because I know you can't see, but for me to make it so that you can see it, I have to keep lifting up the book, and the book's very heavy. Anyway, r is rho sine phi from trig. R is rho sine phi. Okay. Now, I know you probably can't see it now, but from polar coordinates, x is r cosine theta. But here's r, rho sine phi. Y was r sine theta. And there's r, rho sine phi sine theta. And z is rho cosine phi. Okay, in a nutshell, box 1, put that in your next cheat sheet, page 1046. X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And you can see from the three-dimensional Pythagorean theorem, rho squared is x squared plus y squared plus z squared. Rho squared equals x squared plus y squared plus z squared. All right, so box 1 and box 2, put in your next cheat sheet. Okay. All right, next. Triple integrals with spherical coordinates. Okay, so rho, they got E there on page 1047. Rho goes from A to B, distance away from origin. Theta is an angle. Theta goes from alpha to beta. That's the same theta as you had in cylindrical coordinates, i.e. polar coordinates. But now phi goes from, say, C to D. So phi, starting up at the top, okay, it might have one angle here, moving to another angle here. Okay, so that's the way phi works. So here's the little delta V this time. Okay, so that's the spherical wedge that they have. Okay, now we know how to find the volume of a box, length times width times height. And you look at it and say, that doesn't look like a box. That's right. But again, the same idea, if delta rho, delta theta, and delta V delta phi are very, very small, it looks more and more and more like a true box where I can use length times width times height. Okay, not sure I'm going to go over all the details of it. This picture might be a little bit better. Okay, but you see there's a d rho, tiny change in rho. Okay, down at the bottom, you see d theta. Okay, so going up above, that piece there that says rho sine phi d theta, that's the length of that piece there. Okay. Rho sine phi, that's the same thing as r. Where'd it go? Yeah, right there, r. So that piece there, rho sine phi d theta, that's like r d theta. That's the same as the r d theta we had before in the last section. That's the length there. And the other one, see where it says rho d phi? That's the third dimension. That's another arc length. So remember, we're using the formula S is equal to r theta. Arc length is r times the theta, or d theta as the case may be. So see that arrow that's pointing to rho d phi? That's that arc length there. The other one that says rho sine phi d theta, that's the same as r d theta from last time. And then you have a d rho. Multiply them all together. You have a rho times another rho, which is rho squared. You have a sine phi, and then a d rho d theta d phi. That's your little delta v. All right, so bottom line, whether you understood that or not, put this on your next cheat sheet, page 1047. How do you do a triple integral in spherical coordinates? Spherical coordinates. Okay, triple integral of x, y, z, dv. Okay, so change x to rho sine phi cosine theta. Change y to rho sine phi sine theta. Change z to rho cosine phi. And now dv, you have to multiply by an extra rho squared sine phi. I'll go like this. See that at the end? That's dv. Rho squared sine phi, d rho d theta d phi. And sorry, I got to put the book down for rest. Okay, so last time, remember you had to multiply by an extra r, right? So dA is either dx dy or dy dx or r dr d theta. Okay, so dv, well, the rectangular was the easiest, right? You have dz dy dx in some order. Okay, cylindrical coordinates, again, you have to multiply by an extra r. So it was r dz dr d theta. For spherical, when you switch to dv, you always have to multiply by an extra rho squared sine phi. It comes from this picture or this picture, but if you don't get that, just be able to use the formula. Multiply by an extra rho squared sine phi, d rho d theta d phi in some order. Okay, so that's how you evaluate those integrals. All right, so I'm ready to start doing some problems, which means I'm not going to carry the book that much anymore because it hurts or it's heavy. Yeah, I'm still going to experiment here a little bit, but not sure. All right. Okay, so we're starting 15.8. 1 to 11 odd, 17, 19, 20, 21, 23, put in 27. Okay, to give us a point in spherical coordinates, 6, pi over 3, pi over 6. So I have where it is in space. In fact, the last thing you do, even though you write it as rho theta phi, the last thing you do is the rho. You can't start with the 6, right? You start with the 6. Well, which way do I go for the 6, right? Is it that way or that way or that way? So the last thing you do is the rho. Okay. You start normally first with the theta. Okay. So theta in standard position. Okay, 60 degrees there, right? Then phi, 30 degrees down from the top. So I come down 30 degrees, that's pi over 6. So you have a direction. Now I walk out 6 units. That's a pi over 6 here. So that's the point in space. Okay, so 2 angles, pi over 3, 60 degrees. From straight up, come down pi over 6, 30 degrees, and then I walk out 6. All right, so what is that point in ordinary x and y? Okay, so I basically just plug into the formulas. So x is rho sine phi cosine theta. So 6 sine of pi over 6 cosine pi over 3, 6 times 1/2 times 1/2. That's supposed to be 1/2 there. 6 times 1/2 times 1/2, 3 over 2. Y is rho sine phi sine theta. 6 sine pi over 6 sine pi over 3. 6 times 1/2. Sine of pi over 3 is radical 3 over 2. 3 radical 3 over 2. And then z is rho cosine phi. 6 cosine pi over 6. 6 times radical 3 over 2. Cosine of 30 degrees is radical 3 over 2. 3 radical 3. Okay, so the point in spherical coordinates, 6 pi over 3 pi over 6 in spherical coordinates is the same as our ordinary rectangular coordinates of 3/2, 3 radical 3 over 2, 3 radical 3. Okay. So that was 1A. Okay, 3, they give you the point in rectangular coordinates, and they want you to come up with it in spherical coordinates. So this was 3B. Should have put a B here. 3B. If I can write the B. 1, -1, negative radical 2. Okay, so that's 1 out, 1 back. That's right. So I'm going back into the page, 1, right 1, and then down radical 2. So that's the point. All right, so the first thing I'm going to do is find rho. That's easy. Rho squared is x squared plus y squared plus z squared. So rho is a square root of -1 squared is 1, plus 1 squared is 1, plus negative radical 2 squared is 2. So I have the square root of 4, which is 2. So I'm 2 units away from the origin. What do I do next? Okay, normally the best thing to do after that is to find phi, because it only involves, or z only involves phi, right? X and y in the formulas involve theta and phi. Z only needs phi. So the easiest thing to do next is normally to just figure out from the z, okay, rho cosine phi. So z is rho cosine phi. We now know that the z was negative radical 2, right? Rho is 2. Divide both sides by 2. Cosine of phi is negative radical 2 over 2. That's a second quadrant angle. So I come down past the xy plane and go into the negative realm. So theta is 3 pi over 4. So the angle that you go down is 3 pi over 4. Okay. And just to let you know, for a point in standard position, there's never any reason to have an angle more than pi radians or 180 degrees for phi. Okay, so if you stop and think about it, so you start here, going straight up. Yeah, it's a lot better if we met face to face. Okay, but here you're at 0 degrees or 0 radians, right? If you come down 90 degrees or pi, then you basically have the xy plane. Okay, so if you turn theta any which way, you're at the xy plane. If you go to 180 degrees or pi radians, then you're heading straight down. And then there's no reason to go any more than that, because you could have gotten an equivalent angle less than 180. Okay, see if I can show you what I mean. Okay, so if I start up here, 0 degrees, 90 degrees, I'm at the XY plane, right? Pi radians, pi over 2, I'm going straight down. Let me talk about degrees, 180 degrees. Okay, if I keep going to 190 degrees, so I'm at 190 degrees, you didn't have to do that because we could have just come the other way and use 170 degrees. I don't know, does that make any sense? Maybe it makes more sense if I go all the way to 270 degrees. Okay, so if I go like this and I come all the way like that, okay, XY plane, keep going. If we go to 270, I'm back at the XY plane. Well, I could have just come down 90 degrees this way in the first place, right? So there's never any reason that we have to go beyond pi radians or 180 degrees for phi. Okay, so if I go look straight up, that's 0. Okay, if I'm going straight like that, that's 90 degrees or pi over 2. And if I'm looking straight down, that's 180. And again, there's no reason to go beyond that. Okay, so see if I can aim it for you like that. 0, 90, 180. And if I keep going, well, I didn't need to do that. I could have just come down this way. If that makes any sense. Again, it's a lot easier if I showed it to you face to face, but hopefully that made some kind of sense. But anyway, there we go. All right, so phi is now 3 pi over 4. And now that I have that, I can plug in the rest. So x is rho sine phi cosine theta. I now know that rho is 2. Phi is 3 pi over 4. So I have the sine of 3 pi over 4. Sine of 3 pi over 4, I'm in the second quadrant, that's radical 2 over 2. Cosine theta is equal to -1. Clean this up. So the 2's cancel out. I have radical 2. Divide both sides by radical 2. Cosine theta is -1 over radical 2. What second quadrant angle is that? That's also 3 pi over 4. Okay, so the angle you're going at comes all the way back there. Okay, so in spherical coordinates, the point -1, 1, negative radical 2, and rectangular coordinates is now 2, 3 pi over 4, 3 pi over 4 in spherical coordinates. Again, the last thing you really do is the 2. So 3 pi over 4, just think of your regular XY plane. And maybe I'll go like this. Okay, XY plane. So 3 pi over 4 would be like that, right? 3 pi over 4. That's what this is representing. So, and you swing back into there. And phi, you start at the top and come down 3 pi over 4. So you are below the XY plane. So you're going through the ground, as it were. And then you walk out 2 units. So that's what you have. Okay, so once more, -1, 1, negative radical 2 in rectangular coordinates is 2, 3 pi over 4, 3 pi over 4 in spherical coordinates. I'll do my focusing thing again at the end, hopefully. Okay. Just mention off to the side, you might think this is a pretty strange coordinate system, okay? But when you stop and think about it, if you're an astronomer and you're looking at heavenly bodies and so on, you really just want angles. You might not be that comfortable with rho. It doesn't really matter, the rho. How far am I away, right? So many light years. Okay, like you see a star in the sky, or Jupiter, or Mars, or whatever, right? You don't really care that much about the distance, but you want to say, where is it, right? So you could have a certain set 0 degree mark, let's say, you know, heading toward the equator or whatever. So you turn, okay, I mean, it's better than saying, oh, look over there. Where's there? There, where's it, right? How do you aim it? A very specific way is, all right, so imagine you're on the ground level. Okay, you've designated something as 0 degrees. Okay, maybe it's heading toward the equator. Okay, so you turn this way, right? Okay, you see the star. Okay, it's right over here. Okay, and now you want to ask, what angle do I have this way, right? And that designates the star or planet or comet or whatever, doesn't it? Okay, so where is it? You don't really care too much about the rho, right? How far away are you? You know, so many millions of miles, so many light years. Okay, I mean, you see it, it's right there. What you do need to know is where in the celestial sky do you see it, right? So you have to turn your body this way, right? So you have a theta and then a certain phi, right? Although phi is kind of awkward. Normally, what most astronomers do is angle of elevation going up this way, but you could start at the top and come down. And so you can designate an object in the sky, even though you don't even know the distance and you don't care about the distance, you can designate it with two angles, right? How much do I turn this way, right? Okay, I got to turn my telescope this way, this way. Oh, there it is. Okay, so this way. And now what's the angle I got to go this way? 55 degrees or whatever. So from home position, 0 degrees. Okay, I don't know, turn 102 degrees here. Okay, stop. And then you go 55 degrees there. And there it is. There's Mars, or there's Alpha Centauri or Jupiter, or whatever you want to look at, right? So the spherical coordinate system is not all that weird. Okay, and you don't even know the distance away necessarily, but you don't care. Okay, but you can find that star, that object, with two things, two angles, right? How much do I turn this way? How much do I turn this way? Is that right? Okay, then we have some problems that ask you to tell what we have. Okay, describe the surface that's given. So number 5, phi equals pi over 3. Because remember, phi, pi over 3, 60 degrees from the top. So remember, you don't start here, which is natural for you and for me, because our eyes are like that. You have to pretend your eyes are at the top of your head. So you have to pretend you start here, right? This is 0. Phi is pi over 3. You come down 60 degrees. Okay. Now, coming down 60 degrees, that's all it says. Now, let rho go to any number, 0 to infinity. So I got my ruler. It just goes as far as you want. And then theta can move. So can you see if theta moves like so, you cycle around, you end up with this cone, or technically the text calls it a half cone, because a true mathematical cone has a bottom part. But sometimes we call that cone. I mean, we have a formula for a cone. The formula for a cone looks like that. So I'll just call it a cone. All right, so phi equals pi over 3 looks like that. Okay. So starting from the top, can you imagine you start at the top, come down 60 degrees. Let phi go to any number. So phi is 0, 1, 2, 3, 4, a million, a billion. And then theta swings around from 0 to 360 degrees. So you end up with a cone. Okay, number 7. Let's see. Yeah, number 7 says rho cosine phi equals 1. Okay, that's the exact formula for z. So this is z equals 1. What does z equal 1 look like? That's a plane parallel to the xy plane. It's actually just 1 unit above the xy plane. Okay, so take the plane of the floor, come up 1 unit, z equals 1. Now go anywhere that you want, x and y. Or imagine you're on the first floor, right? In the first floor of a building, go anywhere you want this way, just don't go up or down. Okay, and you're describing a plane. So this is in some sense the first floor. Okay, well, I should say up 1 level, because depending, and I know Americans talk differently than the British maybe, but when you say first floor, that might mean ground floor, right? So this really means 1 floor up, I guess, which most of us would consider the second floor, I suppose. But anyway, one unit above the XY plane, and that's what we're talking about. Okay. Okay, 9b, change to spherical coordinates. All you do is just throw it into the formulas. X squared minus y squared minus z squared equals 1, which I believe is called a hyperbola of 2 sheets, but you don't have to know that because there's 2 negatives. Okay, all you do is change x to its formula, rho sine phi cosine theta squared minus y squared, rho sine phi sine theta squared, and then z is rho cosine phi squared. And then I just cleaned it up. Factored out a rho squared, sine squared phi cosine squared theta minus sine squared phi sine squared theta minus cosine squared phi equals 1. And that's about it. Okay, and then 11. That's just to sketch the solid described by the given inequalities. I'll show that quickly. 11. Rho is less than or equal to 1. Phi is between 0 and pi over 6. Theta is between 0 and pi. Okay. It's easier for me to draw the entire cone. Okay, so you're as much as 1 unit away from the origin. So between 0 and 1. So it's not going out to infinity. Okay, and now this is where I have to ask you to just use your imagination. Phi is between 0 and 30 degrees, pi over 6, right? So again, that's starting up here, come down 30 degrees. And now if theta were allowed to go all the way around, we'd have a full cone. Theta, however, is only going from 0 to pi, so you have a half a cone. So you're really only going from there to, so see theta, it's not going all the way around. It's only going out to there. So I didn't draw the picture very well, but you have to think that you have half the cone. Okay, so you take your ice cream cone, split it in half straight down like that. And then, you know, it's not very stable. The ice cream won't be stable, it might fall apart. But if you can imagine such a thing, that's what you would have. Okay, well, you can see the whole cone, right? If theta goes from 0 to 2 pi, because theta is only going from 0 to pi. So just go from there to there, you have half the cone sliced this away. I know it's unnatural because we normally don't cut ice cream cones like that because the ice cream would start leaking, right? But if you cleave it like so, that's what we got. All right, and then we're ready for some triple integrals. Okay. So 17. Okay, so find the volume. 0 to 3, 0 to pi over 2, 0 to pi over 6. Rho squared sine phi, d rho, d theta, d phi. So if they're asking for volume, it's automatically always that. Put that in your cheat sheet. Rho squared sine phi, d rho, d theta, d phi. All right. Fortunately, these are all constants. So there's no theta involved. So I can just take out the length of the interval. So I can lose the d theta. The length of the interval is pi over 2. So there's the pi over 2 for the theta. So I'm integrating rho squared sine phi. So if we integrate with respect to rho first, that's rho cubed over 3. Sine phi is considered constant. From 0 to 3. So plug in 3, plug in 0, you get 0, right? Plug in 3, you get 9. So now I have 9 pi over 2 outside. And I'm integrating from 0 to pi over 6 of sine phi d phi. So that's pretty easy. Integral of sine is negative cosine. Negative 9 pi over 2 cosine phi from 0 to pi over 6. So negative 9 pi over 2. Cosine of pi over 6, cosine of 30 degrees is radical 3 over 2. And let's see, cosine of 0 is 1. That's sort of the answer, but you can make it nicer if I distribute the negative onto here, because that's a negative number. Radical 3 minus 1 is also, radical 3 over 2 minus 1 is a negative number. So distribute the negative here and turn that around. So the best way to write the answer is 9 pi over 2, parentheses 1 minus radical 3 over 2. So that's my answer. Okay. By the way, I intentionally didn't give you that many problems because sometimes they can get real long. 19 and 20. Set up the triple integral of an arbitrary continuous function f of x, y, z in cylindrical or spherical coordinates over the solid shown. Okay, so look at 19. That should definitely be cylindrical coordinates, right? Z is going from 0 to 2. The R is 3. Okay. So if we swing this away, R is going from 0 to 3. How about theta? Look at that block. Theta goes from 0 to pi over 2. It's 1/4 of the way around. If I go all the way around, it'll be 2 pi. You're only in the first octant, right? So R is going from 0 to 3. Z is going from 0 to 2. Theta is going from 0 to pi over 2. So what's it going to look like? Right, so f of x, y, z becomes r cosine theta, r sine theta, z. And remember, in cylindrical coordinates, you need an extra r. So r dz, dr, d theta. And z went from 0 to 2. R went from 0 to 3. Theta goes from 0 to pi over 2. Okay. All right, I'll show you 20, and then maybe we'll break after that. 20 almost looks like a hollowed out igloo or something like that. Okay, that looks like it's spherical. Where does rho go from? Hint, it's distance from the origin. Rho goes from 1 to 2, doesn't it? There's stuff from 1 to 2. How about theta? Okay, you wouldn't be able to see it, but if you went all the way around, it'd be all covered. We're basically losing the first octant, right? So we're starting here, which is pi over 2, and then we go all the way around to 2 pi, right? So we don't have the first octant. So theta is going from pi over 2 to 2 pi, right? You're not in the first octant, which in the XY plane is the first quadrant, but you have second, third, and fourth quadrants. Okay, now what about phi? It stops at the XY plane. So phi goes from 0 to pi over 2, 90 degrees, doesn't it? So it's going like this. Goes straight up here, and it comes down to z equals 0, the XY plane. Because there's nothing below ground level, so to speak. It would look kind of weird, but it stops at ground level, something that we're used to. So phi goes from 0 to pi over 2. So here we go. So phi goes from 1 to 2. Theta goes from pi over 2 to 2 pi. Phi goes from 0 to pi over 2. And then f of x, y, z, x is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And then dv. dv is rho squared sine phi, d rho, d theta, d phi. And there we go. Okay, so I'm about to take a break, but let me do the focusing thing again. So let's see if I have to play with this a little bit later to see if I can get it to work, but maybe I'll wait until after class. I notice I have to move the paper closer than I'm used to in order for it to focus. Whoops, I'll be able to show you that also. There's 19 and there's 20. Hopefully you can see 20 all the way there. And that's it. Okay. All right. So we'll break into our usual 7:10-ish. Okay. All right. Break time. All right, folks, let's try to pick up where we were. Okay, again, those of you who joined late, please put your name in the chat so I can get you for attendance later, eventually. And yeah, I know the focus is not real good, but I'm trying to do this raising up thing, and it's not the way it was before. I must have knocked the camera or something like that. By the way, I am on schedule to get a new document camera for next semester, hopefully. So then I don't have to fool with this anymore, but we'll see. All right, so I was going to do some of the triple integrals. Maybe depending on the time, I think it might sneak in a little bit of the next section, but not sure how much I'm going to do with under these blurry conditions. But I won't go that much longer, hopefully, and then give you the quiz and call it a day. All right, so evaluate the integrals using spherical coordinates. 21, triple integral over b, x squared plus y squared plus z squared dv. B is a ball, center of the origin, and radius 5. All right. So if you have a sphere, center of the origin, radius 5. So x squared plus y squared plus z squared, that's rho squared. So I have rho squared squared times dv. dv itself is rho squared sine phi, d rho, d theta, d phi. Now, here's an important point that kind of goes along with what I said earlier. Okay, we know rho goes from 0 to 5. Theta goes from 0 to 2 pi, going all the way around the circle. But phi only goes from 0 to pi, not to 2 pi. Okay, so again, you get the entire sphere. If you start at the top, okay, come down to the XY plane and then go down 180 degrees, you're looking straight down, and you got everything. Okay, so turn like this again. So 0 degrees, 90 degrees, 180 degrees. There's no need to keep going into 190, 200, because you could have just gone through an angle this way, less than 180. See? So again, normally if you have a sphere, okay, the rho equals whatever. Theta goes from 0 to 2 pi, but phi only goes from 0 to pi. That's a key thing here. Okay, other than that, that shouldn't be that big a deal. So that's going to be rho to the 4, rho squared. So rho to the 6, sine phi. There's no theta in here, and this happens a lot under these conditions. There's no theta, so take out the theta. The length of the interval is 2 pi. Take that shortcut whenever you can. So I'm integrating rho to the 6, integrating rho to the 6 sine of phi. So that's rho to the 7th over 7. As rho goes from 0 to 5. Plug in 0, you get 0. Plug in 5, you have 5 to the 7th power, which comes out to be 78,125 divided by 7. Take that constant out. And then you're integrating sine of phi d phi. So that should be no big deal. Integral of sine is negative cosine. See, 2 times 78,000 blah, blah, blah is 156,250 pi over 7. Okay, so integrate from 0 to pi. All right, and you plug in pi, you get negative, okay, this negative comes here, negative 1 minus cosine of 0 is 1. So I have negative all that times a negative 2. So finally, 312,500 pi divided by 7. So that's the answer. Okay, and I just mentioned quickly, if you had integrated from 0 to 2 pi, that's going to be 0. So you might think, oh, phi should go from 0 to 2 pi. Well, that means you're swinging all the way back around, which you don't have to. And if you end up doing that, you'd end up integrating 0 to 2 pi for either cosine or sine. That's automatically 0. So you know that can't be it. So that's what we have here. Okay, 25. Okay, triple integral of x e to the x squared plus y squared plus z squared. What's x squared plus y squared plus z squared? Rho squared. Okay, it's the unit ball, x squared plus y squared plus z squared less than or equal to 1, unit sphere, but it's only in the first octant, it says, problem 25. So here's the first octant view. All right, so I'll substitute. X is rho sine phi cosine theta by formula. E to the rho squared. dV. Again, dV is always rho squared sine phi, d rho, d theta, d phi. Okay. I ended up skipping it because it's too long. But I do want to go over what the limits are. So show you that. Okay, rho is going from 0 to 1. You're only in the first octant. So if you're in the first octant, theta goes from 0 to pi over 2. Phi also goes from 0 to pi over 2. Okay, so I mentioned that just for the setup, but the integral doesn't look very fun at all. Okay, and you're going to have an e to the rho squared and there's a rho cubed, so not fun. Okay. Yes, that does mean I'm not going to give you this very problem, but I might give you something similar. I mean, I might give you this same picture, but then the function might be easier to integrate compared to this. Okay, 27, and now I'll be done. It's only about 7:20-ish. So yeah, maybe I'll sneak in very little of the next section just to make it things easier next time. I'm kind of hesitant to go too far until I kind of get this camera done. So 27, the one that I'm adding on. Excuse me. Find the volume of the part of the ball rho less than or equal to A that lies between the cones. Phi is pi over 6 and phi is pi over 3. Okay, so you know automatically phi goes from pi over 6 to pi over 3. Rho is going from 0 to A. And they don't say anything about theta, so that means you've got the entire circle, as it were, meaning going from 0 to 2 pi. Okay. So here's the important information. Rho is less than or equal to A, which means you're integrating from 0 to A. Phi's between pi over 6 and pi over 3, they said that. But you are going all the way around a circle on the xy plane. So theta is going from 0 to 2 pi. And it does say volume. So volume automatically is rho squared sine phi, d rho, d theta, d phi. Okay. These are all constants. By the way, A is considered constant in this problem. It's a particular value of rho. Doesn't matter if it's 7 or A, it's a constant here. Okay, so this thing doesn't depend on theta. So take out the 2 pi, length of the interval, 2 pi. Integral of rho squared d rho. Sine phi is a constant, leave it alone. Rho cubed over 3 from 0 to A. Plug in 0, you get 0. Plug in A, you have A cubed over 3. Pass that outside the integral. 2 pi A cubed over 3. Integral from pi over 6 to pi over 3 of sine of phi d phi. So that should be pretty straightforward. Integral of sine is negative cosine. So cosine, I put the negative over here. Negative 2 pi A cubed over 3. Cosine of phi. Cosine pi over 3. Cosine of 60 degrees is a half. Cosine of 30 degrees, pi over 6 is radical 3 over 2. Okay. And again, that looks backwards. So I switch it around. And by the way, you can cancel that 2 with each of these 2's, right? That 2 cancels both of these. So I have just negative pi A cubed over 3, 1 minus radical 3. Distribute the negative over here to make it look better. So final answer is pi A cubed over 3 times radical 3 minus 1. And there we go. Okay, and let me go back and do my focusing job again. I know it's not the location where it was before because I have to raise the paper a little bit higher than usual. So sorry about that. But again, yeah, you should be able to see this better in the video. and 27. Right, so that's that. So mission accomplished in some sense that I was able to finish spherical coordinates. So I am done with 15.8. So the only section we have left for this upcoming exam is 15.9. I'll sneak in a little bit and then I'll stop and give you the quiz and we'll call it a night, especially under these strange conditions. Not sure if I can get this thing back to the way it was, but we'll see. So I'm going to go ahead and mark 15.9 a little bit today. So in all likelihood, I'll conclude 15.9 on Tuesday, the 13th. Okay, so we should plenty of time. We're not going to change the date of the exam, still on the 22nd, but that does mean I'll get started with our last chapter, chapter 16. Okay, so 15.9, introduction. Change of variables in multiple integrals. By analogy, what do we do in Calc 1 and Calc 2 when we did a U substitution, right? So maybe I'll make up a problem, but you won't be able to see what I got, I guess. So let me see if I can make up something fairly easy. Integral, yeah, I know you can't see it, but bear with me. Oh. Integral of x cubed plus 1 to the 4th power 3x squared dx. Remember doing substitution, right? Do a U substitution. And let's see, what should I pick so I don't get something too bad? From 0 to 2. So originally on your number line, you're integrating from 0 to 2 some function. You're finding this area, right? Okay, do a U substitution. U equals x cubed plus 1. Du equals 3x squared dx. Yes, we were doing a lot of this semester kind of fast, so we wouldn't have to do all the U substitution, but here I really want to do it. So that's going to be u to the 4th. That's going to be du. And these limits change also, don't they? So when x goes from 0 to 2, what happens to u? So x equals 0, u equals blank. X equals 2, u equals blank. Okay, so I plug in 0 to 2. So what do you get when you plug in 0? 1. What do you get when you plug in 2? 2 cubed is 8 plus 1 is 9. So my new integral isn't going to go from 0 to 2. It goes from 1 to 9, does it not? So the new integral, which I'll call I know you can't really see it yet, integral from 1 to 9 of u to the 4th du. And then just take it from there. And I can see the numbers aren't going to come out nice, but that's all right. U to the 5th over 5 from 1 to 9, which is 1/5 of 9 to the 5th minus 1 to the 5th. And I'll just leave it there. I don't care what 9 to the 5th power is, but you get the idea. Right? So you all remember doing stuff like that, right? Now here's the whole idea. So the interval, which used to be from 0 to 2, by means of this transformation, this change, since u is x cubed plus 1, the new integral went from 1 to 9. because u equals x cubed plus 1, right? The original picture, oh yeah, here's the function. I'm integrating from 0 to 2. By making use of this substitution, I'm no longer going from 0 to 2. Because they're related this way, u equals x cubed plus 1, the new integral goes from 1 to 9. Is that right? It's like the interval changed from 0 to 1, 9. An interval changed to a different interval. Okay. What's happening now in multivariable? Oh boy. In general terms, in the xy plane on page 1053, maybe your original integral looks like that, and you transform it and it looks like that. We're not actually going to do anything that bad, but they're just speaking generally. That's in 2D. And of course, you can apply this to 3D. So what happens in 1D, right? You have one interval to another interval, right? The one that I just showed you, instead of going from 0 to 2, the new one went from 1 to 9. In 2D, you might have, by the transformation, that yellow region going to the blue region. That letter T stands for transformation. That's like, u equals x cubed plus 1 that I was doing over there. There's actually something that might happen in a real example. See that square region, the yellow? After you transform it, maybe it looks like that. So again, very rich in the possibilities that you have once you get to multivariable calculus compared to Calc 1 and Calc 2. You just have one interval from A to B, and then after you transform, it's a new interval from C to D. Okay, and if you want to, you can actually work all these out, but see those lines in yellow? See where it says S1, S2, S3, S4? Okay, they've got 1 arrow, 2 arrows, 3 arrows, 4 arrows, right? The transformation goes to that. So see that one yellow arrow? It becomes that blue arrow. The 2-line one, the one that goes straight up, becomes that curved arrow, two arrows. 3 arrows from right to left becomes that 3 arrow going down. And then S4, those 4 arrows match the 4 arrows on the bottom. That's how the transformation works in multiple variables. Okay, these can get real long. And by the way, this is only 2D. Okay, you can make it much worse in 3D. Okay, so it's very rich, as I said. So that's the reason why I only, quote unquote, gave you 1 to 17 odd, skip 11. Some of them are already bad enough, but if you wanted to make a problem real bad, you can make it real bad. Okay, I tried to make ones that are, quote unquote, not too bad. All right, a little bit of background theory. So there was a multiplication factor. So, when you switch from dx to du, you can't just change dx to du. There might be a multiplication factor, right? Like in the one I just showed you, it was a 3x squared. In other words, you're not allowed to just change du to dx. They're related in somehow. So maybe 3x squared dx. Okay, so you can't just change du to dx. You have to multiply it by something, 3x squared. So likewise, when you change something in 2D or 3D or however many dimensions, you can't just change a d something to d something. You have to multiply by something. That something is called the Jacobian. Page 1055. It's a multiplication factor when you convert from one system to another system. Okay. Now, I'll sort of quickly go over this because the book is heavy. All right, see that region R there? They've got vectors A and B. So when you transform let's say dx dy, 1 unit, into say du dv, you're not necessarily going to have the same area. Okay, but you can have, they put r sub u and r sub v. For these planar regions. Again, you say it doesn't look like a plane, but same thing. As we always say, if delta u and delta v, which are representative of the change in x and y. So if we're changing x, y to u, v, just like before we were changing x to u, we're changing x, y to u and v. So we have a delta x and delta y becomes a delta u and delta v. That's what he's trying to show you there. There's going to be a change in area. That extra multiplication factor. Okay, well, it's going to be an r sub u and an r sub v. That changed area, we can find the area of that parallelogram by doing ru cross rv. Okay. The k component is 0 because we're in xy plane. And so if you work all of that out, you get that determinant over there, okay, which ends up being that minus that. Okay. That thing is called the Jacobian. Okay, so definition of Jacobian, put this on your next cheat sheet. It looks like the partial of x, y with respect to uv. So what's happening? You have x equals g of uv, y is h of uv. Something called the Jacobian. It looks like the partial of x, y with respect to uv. It is. You take everything on the top and differentiate with respect to everything on the bottom. So see that determinant? It's got partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v, which is by the normal two-dimensional determinant. It's that times that minus that times that. So see, it's the partial of x with respect to u times the partial of y with respect to v. That's going across this way. That times that minus that times that. The way we normally do 2 by 2 determinants, right? So the other one was partial of x with respect to v times the partial of y with respect to u. That's a Jacobian. That's the extra multiplication factor that you need when you change from one to the other. That's just like this. In fact, it would not be that much of a stretch to say 3x squared is the Jacobian in one dimension. Okay, you can't just change du to dx. They're related in some way. So, oh, du is 3x squared dx. So this thing is sort of like the Jacobian. I'll put it in quotes because we don't really call it that in one dimension, but it's the equivalent of the Jacobian. It's the extra multiplication factor. Because when you transform from one to the other, you're no longer going to integrate from 0 to 2, right? You might integrate from 1 to 9. So likewise, when you make the transformation, that square region ends up looking like that region. It's going to be a bigger dA, bigger change in area. How do you get the change in area? The Jacobian. Okay, now there's an equivalent three-dimensional Jacobian. And where do they show you that? Page 1059. Three-dimensional Jacobian. As you might guess, it's just one higher dimension. Partial of x, y, z with respect to u, v, and w. So notice along the top, it's all x. Second row is all y. Third row is all z. If you look at the columns going down, the first one is u, the second one is v, and the third one is w, right? It really means take all the variables on the top, x, y, z, differentiate with respect to all the variables on the bottom, u, v, and w. So partial of x with respect to u, v, w, partial of y with respect to u, v, w, partial of z with respect to u, v, w. And you work on that 3 by 3 determinant. Okay, so let me show you what's going to happen in the integration. So you want this on your cheat sheet, page 1056. double integral of f of x, y, dA. You're given some transformation. Change x and y to u and v. You're going to be given some root. That's just like when we said, let u equal x cubed plus 1. A single variable to a single variable. X changes to u. Now, two variables change into two variables, right? X and y change to u and v. So notice dA. dx dy becomes du dv, but you have to multiply by the Jacobian right there in the middle, partial of xy with respect to uv. Okay. So again, the Jacobian is defined by this thing. And this gets a little, sorry, I misspoke. This is where the bars, see those bars, those are not absolute value bars, right? It's the evaluation of a determinant. So when you write the Jacobian, see how it's just partial of xy with respect to uv? There's no bars there. There are bars here. So that means absolute value. Absolute value of the Jacobian. Okay, just to let you know, I will abbreviate Jacobian with a capital J, so I don't have to write that whole thing. Okay. So here's dA. So another way of having dx dy or dy dx is Jacobian times du dv, where u and v are given to you. That's equivalent to one dimension, right? We change x to u. That 3x squared is the so-called Jacobian. Two variables. Change x and y to u and v. It becomes a du dv times the absolute value of the Jacobian in front of it. So that's kind of like the 3x squared that I just showed you. Okay, so put that on your cheat sheet, page 1056. Then three-dimensional flavor on 1059, you just add another dimension. XYZ, change it to UVW, number 13. And you have a three-dimensional Jacobian. Again, that's absolute value, partial of XYZ with respect to UVW, du, dv, dw. Those can get really, really long. So I don't think I gave you any of those. I'll have to check. Okay, I think I had you compute one of these three-dimensional Jacobians, but not actually work out a full problem because it gets really long. The two-dimensional ones are already long enough. Three-dimensional one just gets super, super long. Okay, but that's in theory what you do right there. Okay, and I think those are all the formulas that we have for 59, and I'll start doing that next time. So, right, so again, what you need is a two-dimensional definition of Jacobian, page 1055. Yeah. There's no formula for the transformation per se. Okay, they can get really long. Like, how do you change that rectangular region into that region, right? So we'll do very few. Okay, we're doing actually extremely few problems, just the quote unquote nicest ones, but it can get really bad. And then you want to be able to use a three-dimensional Jacobian. 3x3 determinant. And then box 13, although frankly, I don't think I'm going to give you anything that bad. So you can probably get away with not doing 13. It's just way too long. Okay. So next Tuesday, I'll get started with that. But otherwise, I'm done and I'm ready to give you the quiz unless anybody has any questions about something. Okay, so does anybody have any question? You can either unmute yourself or put it in the chat. Otherwise, we'll go to our quiz and that'll be it.
You said you're not going to give us any problems on the three-dimensional Jacobian, right?
you will have to compute a three-dimensional Jacobian, but not a triple integral.
Okay,
It's probably going to be too long.
okay, got it.
Okay, anybody else, please? All right, quiz time. Get your cell phones out, or if you're ready to do the screenshot. And I'll have to aim it right, unfortunately. Okay. That's not focused, so I'm gonna have to do this in parts, I think. Sorry. Now,
Shoot,
let me try to
see it.
fiddle with this a little bit. Yeah, a screenshot now probably doesn't help that much. Well, I have to do it in two parts, sorry. Okay, I'll read it also. Okay, triple integral over the region E of x squared y z cubed dv. You know, you might be better off just writing it instead of a screenshot or whatever. Okay, so you're doing triple integral of x squared y z cubed dv. The region is 0, 3 cross 0, 4 cross 0, 2. You should know what that means. First one's for x, second one's for y, third one's for z. And I want you to integrate two ways. Number one, let dv be dz, dy, dx. That's our favorite. Number two, use dv as dy, dx, dz. You don't really need the bottom part, but just from Fubini's theorem, what should be true about the two answers? It should be obvious what the answer to that is, right? Okay, so let me go back and start again. Sorry. So if you want to do a screenshot, you may, but it has to be in parts or cell phone picture, or just write it down. Triple integral over the region E, x squared, y, z cubed, dv. The box region is 0, 3, cross 0, 4, cross 0, 2, x, y, and z. So don't forget, you might have to change the limits depending on which one you're doing, number one and number two, right? So number one, do dz, dy, dx. Number two, do dy, dx, dz, which means you have to change the order of your integral, right? Okay, is there anybody that needs more time in this? Everybody got it?
No, I do think you could hold it up just a little bit more.
Okay, what part do you need, DK?
First, yeah, I need that bit.
Okay, go ahead, get that. Maybe I can show you that now, maybe I can't. X squared,
Okay.
y, z cubed. Oops. Paper's curling on me.
Okay, I got
Okay.
that, and then I got the cross numbers.
Okay, and first one and go, the order is dz, dy, dx.
dy dx, and then the second order is dy dx,
dx,
dz.
dz.
Okay.
All right, anybody else need this, please? You can all fit in the screen if I go like that, but I know you can't really see it. But, well, you're helping each other out anyway, so hopefully if anybody can't see, you can ask one of your mates on that. Okay, I'll assume you have it, so go ahead and get started. I'll set up the breakout rooms, stop share. Else in the chat. Okay, I'm giving you shared screen option also, so if you want to share the screen with somebody, you should be able to do that also, okay?